Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's webinar is ADM 2015 Aluminum Structure Design in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Wieland Gotzer will be your moderator. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So regarding the content for the next hour today, I want to give a brief overview of our standalone program, Shape Thin, our FEA program, RFEM, and the add-on module concept within RFEM. Then we'll move into our example where we will create a custom extruded aluminum section in Shape Thin. This allows us to calculate the cross-section properties as well as the element width to thickness ratio. So you'll hear me say this quite a bit because this information is what we can essentially integrate from Shape Thin into RFEM as treated as any other member. Once we are in RFEM, we will do the complete modeling of an aluminum carport structure. We will load it. We can set up our load combinations according to the ASCE 7 and to run a full analysis. We'll take it a step further and utilize one of our add-on modules, which will provide aluminum member design per the ADM 2015. So with that, I want to quickly go over the program and add-on module concept for those of you who may not be familiar with our programs. And the first program is Shape Thin. This is a standalone, and it is for thin-walled sections where we can manually create these thin-walled sections directly within the program. We can create built-up sections by implementing some of the sections from the ADM or the AISC standard, or we can import in a DXF file, which is what we'll be utilizing today. These section properties will be calculated. You also have the ability to run a basic stress analysis directly within the program, which we won't be taking advantage of that today, but it is an opportunity to do so. Then we take these cross sections along with their properties and we can integrate them into our FEA program, RFEM. So RFEM, again, is a separate program, and this is where we can model our structure entirely. We also can integrate with BIM software such as Revit, Tekla, AutoCAD. We can fully load the structure. We can set up our load combinations, again, according to the ASCE 7, as well as many other international standards, and eventually we get a full analysis. Now, the analysis will provide us with design internal forces, deflections, support reactions, and we can take this analysis information into our own tools to do the design. Now, if we'd like to do design within RFEM, this is where we'd want to take advantage of the design add-on modules. And in particular, today we'll be looking at RF-ALUMINIUM ADM. So this is nothing more than just a dialog box that is within RFEM that allows us to do member design for aluminum per the ADM 2010, the 2015, and we have both ASD and LRFD. This does include both ultimate and serviceability design, so we can check deflections as well. This also includes custom extruded sections, which we'll see today, where we take this section from Shape Thin into RFEM and we can design it per the ADM. Now, this is for unwelded member design. Hopefully, at some point in the future, we hope to add the welded checks, but for now, keep in mind that it is only for unwelded members. So we are going to start off in our program Shape Thin, and I have created in AutoCAD a cross section. And I want to import it in as a background layer within Shape Thin. So how we can do so is just by going to File, Import, and you must save your AutoCAD file with the DXF file extension. So we can simply click Open, and what you'll notice is that we have a dialog box here where we will want to name the section. I'm going to uncheck the plastic cross-section properties. I'm not so interested in that for this extruded section today, but what I do want to check is the C over T parts. Now this is the width to thickness ratios of our different elements that comprise this cross-section. So this includes flanges, webs, any of the lips or extruded sections. Now why this is so incredibly powerful is that when we take this information of these width to thickness ratios into RFEM and eventually into the aluminum design module, we can actually check all of them for local buckling. So this is not something that maybe some other programs can do, but with that requires maybe a little bit more additional work within ShapeThin itself to define this section, and we'll go ahead and see that now. So when I click import, we are brought into our graphical view here where we can go ahead and place the DXF background layer. Now there are a few options here for how we exactly want to place this DXF file. And I'm going to choose this one here where I can further edit it. So I select this center node, I snap here to my origin point, I can right click to exit out of this dialog box, and now you can see this background layer here. Now it's not so simple that we can just simply mesh based on this import here and to calculate the cross-section properties. We somewhat need to trace over this background layer again, and that's to determine the width to thickness ratios for eventually local buckling. But we do have some powerful tools that allow us to actually do that fairly easily. So under edit, we have set elements with DXF template. The first option here is to set the center lines. What I can do is to zoom in and I select two lines, and you'll notice that the program automatically places a center line between the two selection lines. So I'm going to focus for the most part on the left side of the structure here, because once I define my elements on the left side, I can mirror it to the right side. So in addition to setting the center lines, we have this fourth option here to set the elements. So we can manually draw in our elements up here with a new line, but we want to take advantage of these tools that just make our life a little bit easier within ShapeThin. So I want to set my material right now. So I can open up my material database, and you'll see over on the left we have our filters. We can filter to metal, to aluminum, to the ASTM, and eventually the ADM 2015. And we have quite the long list here of all the aluminum materials directly from the standard. Now, if I want to go ahead and search by a particular material, for example, I can type in 6061 and I can see all of the applicable materials here, where I will choose 6061 T6 for pipes and tubes. Now, all of my material properties are defined here. Quite honestly, the material definition is not so important within ShapeThin if you're not doing a general stress analysis, which we're not today. Eventually, once we get into RFEM, we're actually going to have to redefine the material anyway, but this is just a good introduction of where you can find the materials within the database. So now what I can do is just to simply click on these center lines, and the program detects where the outside boundary lines are for the thickness of these elements. So once I have completed, for the most part, the left side of the structure, you'll notice up here, I want to actually drag this one element to the end. No problem. I can just drag and drop it, and it will snap right to that end point. I can highlight all of my elements here and to use my mirror tool. And mirror tool is exactly like what we would find in AutoCAD, for example, where we can create a copy. We can mirror about the global z-axis and the origin point. I click OK, and now the program has created all of the elements on the right-hand side. It does create a couple little small segments here that I can just simply delete with my keyboard. Now, you'll see these symbols at each element, and this is the width to thickness symbols, those C over T parts. So this is what's recognizing width to thickness, but even more so, you'll notice that at these closed ends, we have what's called, looks like a T symbol, but at the open ends, we don't have that same symbol. So this, again, is important for aluminum design to tell the program, okay, how the edges are supported. And over on the right hand side, we can see that it's supported, but over on the left hand side, it's not supported. Again, important for local buckling. When we look at one of these other elements that's supported on both sides, we see that T-type symbol on both sides. So that's all that we need to do, and now we're ready to run our calculation to determine the cross-section properties. So when I go to run the calculation, I will immediately get an error, and it says material number 1 Fy is not positive. So this is the yield strength for my aluminum, and I can immediately look down here to my table, and the program jumps to Fy where it's set to 0. Well, the reason for that is because aluminum has different yield strengths depending on if it's for tension, for compression, for shear. So all we need to do is just to set some type of placeholder here. Fy equal to 30 is perfectly fine. So that's the reason why the program populates 0 there. So we can rerun our calculation, and now we can see that we are presented with our results. Most importantly is if we take a look at table 4.1 for section properties, the program has automatically calculated all of the cross-section properties for us, including area, moment of inertia, warping, things like that. So everything has been done automatically according to my calculation. Now, it's very important now that I save these results. So you have to save the results with the cross-section properties, because in order to integrate in RFEM, we need to know those, and that only occurs with the saved results. We will get a message in RFEM when you try and integrate a shape thin section without running a calculation first. So that's all that is required from the shape thin side. So now what we can do is to jump to RFEM. And RFEM, you'll notice, has a very similar interface to shape thin. So what's great is that if you know RFEM pretty well, then shape thin should come pretty naturally. We want to give this one a name, so we'll call this one Webinar 100. The type of model is 3D. We can generate the load combinations automatically according to the ASCE 7 2016. Now, you can see in this drop-down box, we have many other international standards as well, including the MBC 2015. You can always uncheck this checkbox here, and what this allows us to do is to manually create the load combinations instead. But today we want to take advantage of the load combination generator, so we click OK, and we are brought into our main program RFEM. So to give a quick overview, again, for those of you who are not familiar with RFEM, we have our graphic window right here in the center, and we'll begin to model our structure, and we'll see that built up visually here. Down at the bottom is our table, and we can always import and export data to and from Microsoft Excel. This includes our results that will eventually be presented to us in table format as well. Over on the left is our project navigator. So as we begin to generate this model here, all of my input data, including my loads, my load cases, combinations, will be all available to me within the project navigator so that I can make quick changes to entire cross sections or to entire material groups. If we scroll down a bit further, this is our long list of add-on modules. So this again is why we have the concept only pay for what you use, because quite likely you won't utilize most of these add-on modules depending on the materials or the standards, international standards that you utilize for your projects. And finally, we have our tools up at the top, which we'll be utilizing today. And that brings us to the creation of our first column here, where we will go up to our quick tool here to draw a new member. So when we choose this option, we want to select the member type beam. We can open up our cross-section library. And for aluminum sections, we will probably typically be working with the parametric thin-walled sections, or we can take advantage of the ADM sections directly from the standard itself. So with that, we will choose a hollow square section for today. So I click on my HSS sections, I filter over here to the ADM, and we'll see an additional filter to the ADM 2015. Now, for my first column, I want to select a 5 by 3 by 1/4, and I can just choose it right here in my drop-down box. Now, the material by default when we first open up the program is 4,000 psi concrete or steel A992. So what we need to do is to choose a new aluminum material from our database. Well, that's quite easy by launching our material database, and this should look very familiar. It's almost exactly like what we saw within Shape Thin. We can use our filters over on the left to filter to metal, aluminum, ASTM, and the 2015. Once again, I can type in 6061 and I can select from 6061 T6 from my list here for pipes and tubes. All of my material properties are presented in this table. I click OK, I click OK. And just to also preface this, our model today, everything will be fully fixed, but if you did want to set a pinned member end, you would do so within the same dialog box here by creating a new member hinge. But leaving everything fully fixed, that is what the type none means, so we'll just go ahead and go with that for now. So we want to begin by drawing our column, but I want to change around my drawing grid here to the vertical direction. Well, I can do so by changing my work plane into the XZ plane. I can scroll down, and instead of a straight line, I actually want to create a curved column, and I can do so by selecting an arc here. So I snap to the origin at 0, 0, 0, and then my second point can either be defined on my work plane here, but in my particular case, I don't have exactly 1 foot increments for my second point, which is what the default is for my drawing grid. So what I can do is just to type in the coordinate points directly at 4.42, 0, and 11. Now you want to make sure not to drag your mouse outside this dialog box because as you'll see, everything resets to the current position of my mouse on the work plane. So we'll retype that in at 4.42, 0, and 11. We scroll down here to apply. And now you can either define the radius by once again clicking on the work plane here, or I can just type in 30 feet on my keyboard and hit enter. And so now we should see the curved aluminum column shown here. In a similar sense, we want to go back and draw a new member. And I want to take advantage of the exact same cross section, the same material. I click OK, and we want to create another curved member. So we'll choose the arc option. Now my first point, again, doesn't fall at these 1 foot increments, so I can specify negative 0.5, 0, and 0. I click apply. Now my second point is going to be negative 3.5, 0, and 11, and I can hit apply. Now you'll notice that my radius is actually curving the wrong way. Well, that's no problem. All I need to do is just to check the checkbox for reverse orientation. I'll type in 40 feet on my keyboard and I hit enter. And so now we have our second curved aluminum column here. The next thing to do is to apply some type of intermediate brace between these two columns, and I want to do so at some nodes along the member length that I need to create. So I can right click on my right column and I'm going to divide the member by a certain distance. So with this distance, I have the opportunity to choose the projected direction Z. So what I want to do is to add a node that is 5.5 feet in the vertical direction starting at the base of the column. So you can see here which side is the member start and the member end based on this black arrow here. I type in 5.5 feet for my member start. I click OK. And so now I have divided this member, which has created an intermediate node there. I'm going to do the same thing with the left column. I'm going to right click and I'm going to divide the member by a certain distance. Again, we're going to choose the projected direction, but this time it's going to be 4 feet from the member end. You'll notice that we have the reverse orientation for this column, which is no problem at all. So now we have split apart this member as well. I want to go back to drawing a new single member. And once again, I'm taking advantage of the exact same cross section, the same material. I click OK, but this time instead of the member being a curved element, it will be straight, where I can snap to those new nodes that I have just created to add a small little intermediate brace here. Okay, so moving on to the top of our carport canopy structure, we want to import in that shape thin section. So what I can do is to go to draw a new member, which we are very familiar with, and to open up my cross-section database. And you'll notice that once this populates over on the right-hand side in the very lower corner, we can import the cross-section from shape thin. So when I do this, we will browse to the file location of where I saved my custom cross-section so we can see it here. And by the way, if you were trying to import in a cross-section where the results weren't saved, you would see some type of warning or note like this, just telling you the cross-section hasn't been calculated. Go back to shape thin and do so. So this is why the results need to be saved with the shape thin file. So we can see here section 2 that we have just created. We want to import that in. Now notice when we did that, it defaulted to the first material, concrete 4000 PSI, that we have available in our model. So we actually want to edit the cross section, and instead of concrete, we're going to choose the aluminum material that we've already defined in the model. So it's now always available for any additional members that we create within this file. So I choose aluminum 6061. And we can see here that everything looks okay with the material and the cross-section set now. I'd like to move my drawing grid so that the origin is now placed at the top of the left column. Well, I can do so by selecting this button up here to set the origin of the grid work plane. And I move to the top of the left column. And now I'm still within the dialog box option to draw my new member. So I'm going to choose a point that is about 4 feet away from the top of the column on the left. And we will span about 3 feet to the column on the right. So what's also powerful, if I turn off my drawing grid here and I zoom in, is that we do bring in the exact rendered view of this custom cross section. So it's somewhat nice to see the orientation of the member and how it's framing in to these columns that we have just created. So once we have created this main beam up top, I'm going to hold down my control key and select only my members. So you'll notice that I'm paying careful attention to not select the nodes. But there are a couple nodes that I do want to include. So by holding down my control key, I'm going to select the node at the top of my right column and the rear node. Now there is a specific reason why I'm doing this. I want to go to my Move Copy tool in my toolbar. And move copy, nothing too fancy about this. We want to make 6 copies in the global Y direction of 4.5 feet. And under the Edit Expanded Settings, what we have the ability to do is to create lines between copied nodes. So this is why I was careful to only select a couple of nodes that I was interested in. And even more so, we can assign a cross section to those lines. And we can create a new cross section type by going to a new member. And this should bring us to a familiar dialog box where we can launch our cross-section library once again, because I do want to create a rectangular hollow section here. So I choose this option, and over on the left we will see our ADM filters once again, and I can scroll down in my list to choose a 3x3 by 0.125. I select my material from this drop-down box. Remember, it's already available to us because we have defined it within the model. I click OK. I click OK, and we're back in this Move Copy dialog box. I click OK once again, and what you'll notice happen is that not only did we make copies, but the program has placed these intermediate beams between our copied frames. So it's just taking a step out of the equation where we don't have to manually draw these beams in here. I want to take a few of these main frames, and I'm holding down my control key and selecting them, and I hit delete on my keyboard because they are not necessary. So now we are presented with, for the most part, a majority of our modeling is done with the carport canopy structure. A couple things to add. Number one is that if I wanted to slope this roof at 5 degrees, And normally with sloping the roof, it might be a little bit difficult because we'd have to figure out at what elevation all of these nodes should be placed at depending on their distance away from where the slope should begin. But we do, once again, have a nice feature within RFEM that allows us to do that automatically. So I select all of my roof members here, and under Edit, we have the chamfer tool. So with the chamfer tool, we can define an angle of -5 degrees. We want to rotate it about the global y-axis, and we want to rotate it in the direction of z. Then I can graphically pick the point where I'd like the rotation to begin. So I choose at the top of my right column any one of these points. The program populates the coordinates. I click OK, and now my roof has a 5% slope to it. So again, just a nice feature so that we don't have to manually determine what all these different elevations are based on a 5% slope. The last and final thing to do with modeling of our structure is, of course, to support it. So we can go up here to a new nodal support. Now we have a few default options, including hinged and rigid, pin type support, or fully fixed. We can always create our own type of nodal support, which you'll see are 6 degrees of freedom here for rotation and translation. If you have partial fixity for somewhere in between fully fixed and fully released, you can set that. Or because RFEM is a nonlinear analysis program, you can set these geometric nonlinearities so that perhaps the support fails in uplift, for example, or sliding or friction or anything of the sort with partial activity. For today, we want to choose the default fully rigid option. I click OK. All that I need to do is to highlight across the bottom of my structure, and now those fixed supports are applied to the bottom of those columns. So we are essentially done with the modeling, and we want to move on to loading. And what we need to start off with loading is, of course, defining our different load cases. And we can do so within the option up here to define a new load case. So this will bring up our load cases and combinations dialog box. The first load case to create will be dead load. The action category is set to dead. Action categories are important because this tells the program exactly what load factors to apply to each load case based on the ASCE 7 or whatever standard you're using for the automatic load combination generation. The self-weight is automatically checked here for dead load, but when we create a new load case, and we'll call this one live load with the action category of live, we want self-weight to be unchecked because we don't want to account for it twice. Now, because this is a carport structure, maybe we want to consider the possibility of impact loads. You know, perhaps a car could unfortunately drive into one of these columns, and we want to account for that. So we'll create a couple of additional live load cases for impact. So we'll call this one Impact 1. And the action category is set to live. We can make a copy of this load case and we can rename it to Impact 2. I'm going to create a load case here for Wind 1 with the action category of Wind. And once again, I'll make a copy of this one and create a second load case for Wind 2. Now, of course, you'll probably have many more load cases for your project design, but for today's example, we will just stick with these. So under the Actions tab, this is important because here are my actions that I've defined: dead, live, and wind. Now, under live, I have my live load, which will be some type of area load at the top of my roof structure. I want that to always be acting within these load combinations, but Impact 1 and Impact 2, I don't want everything to act simultaneously as we have it set here. Instead, I want Impact 1 to apply or Impact 2 to apply along with the first live load. So how we can do that is by setting the option for differently here. So live load can be set to no group, Impact 1 can be set to group 1, and so can Impact 2. So now the program will apply Impact 1 or Impact 2. Alternatively, it will not apply them at the same time. It's a similar concept for wind load. Wind loads are automatically by default set to alternatively, so it won't apply wind load 1 plus wind load 2, it will apply wind load 1 or wind 2 within our load combinations. The combination expressions, this is just the program letting me know that it will create LRFD load combinations as well as ASD load combinations. If we have any question about what those load combinations look like, we can click this little info button to see them listed directly from the standard. Now, probably most important is the actual load combinations tab here, because this is going to show me all of my LRFD load combinations in orange and then my ASD load combinations in red. The calculation parameters for load combinations by default is set to second order analysis, considering both big P delta and little p delta for all members. The result combination is nothing more than an envelope solution. So what the program does, it creates a result combination for all of my LRFD load combinations, and we have a result combination for my ASD load combinations. This allows us to maybe graphically or within our tables see the max and min results within all of these load combinations combined. So essentially just a result summary. So once we are done defining our different load cases here, we need to actually apply the loads to the structure. So we're going to select dead load from my drop-down box here. And I want to apply a downward area load to the top of my structure to account for, let's say, some PV panels that will be placed on top of there. Under Tools, we can go to Generate Loads from Area Loads on Members via a plane. So rather than having to manually define what all these different member loads are based on their tributary area, we actually can let the program do that for us. So we choose the load direction in the global Z, which will be the downward direction. We give it a magnitude here of negative 0.02 kips per square foot. And I am going to select my corner nodes here by just graphically clicking on the 4 points. Now we also have the ability to exclude members parallel to a particular member. Now what I mean by that is what I can do is select one of these intermediate beams here, framing in and out of the page. I select one, you'll notice that all the rest are unselected if we do not want the load to be applied to those, but rather our main beams instead. I click OK, and now you can see our area load generated, but even more importantly, if we right click and display separately, we can see the area load magnitude split up for each individual member based on its tributary width. We now want to scroll to live load, and actually it's the exact same concept here. We'll go back to Tools, Generate Loads from Area Loads on Members via a plane. What's nice is that the program remembers all of my settings from the previous application, so all I need to do here is just to change my magnitude to something slightly smaller. I click OK, and now for live load, you can see here the member loads applied based on their tributary area. Now for impact load, this comes from the ASCE 7 2016 and specifically section 453 for vehicle barrier systems. The code tells us that for impact loads, we should consider a 6 kip load applied anywhere between 1 foot 4 inches to 2 feet 3 inches above the floor. So for this application, I want to consider an impact load on my center columns here. I'm going to go to a new member load, and instead of applying a uniform load, I can just change this to a concentrated load. With a concentrated load, we want to apply this in the global X direction, so the lateral direction. We want to give it a magnitude of -6 kips, and we want to apply it 2 feet from the member start. So I click OK. Then I can just click on my column directly to apply that impact load. I scroll to the next load case, impact 2, and you'll notice that my option to apply loads is still active. So I can just easily click on my column for the next load case to apply my second impact load. I right click to exit, and now you can see here as we scroll to the two different impact loads why we wouldn't want these acting at the same time, but rather we wanted either one or the other. Now, of course, maybe we'd want to add some impact loads to our exterior columns as well, but we'll just keep that for the simple application for today. Now for wind loads, we do have a automatic wind and snow load generator. Now the snow load generator would be efficient for this canopy type structure. The wind loads unfortunately cannot be used because we only have partially enclosed and enclosed structure for our wind load generator. Typically for canopies, you would be considered as open structures. So we will need to manually apply our loads for today. So what we want to do is just to go back to the area loads on members via plane in order to apply those. Now, before I do, when we're manually taking a look at these calculations for our wind loads based on open structures, or maybe we have some spreadsheets to do so, I just want to touch on a tool that we have on our website. If you go to dlubal.com and under solutions, you'll see here the GeoZone tool. What we have done is we have integrated the maps for snow, wind, and seismic directly from the ASCE 7. You'll also see here the NBC standard as well as many other international standards. Now, this is also integrated with Google Maps technology. So what we can do with our project, for example, is to type in the location address, or we can click directly on the map. And we're looking at wind for risk category 1 here. We can see that the basic wind velocity is set at 105 miles per hour. So just something that maybe is a little bit more efficient than opening up the code and having to flip through to all those different maps. You can take advantage of this. Keep in mind that the first 10 or so clicks are on us, but if you plan to heavily utilize this tool, then maybe you'd like to buy a package within our web shop. So assuming that we have taken this information, we have determined what our magnitude should be for our structure today, we want to apply this in the lateral X direction. And again, applying this to my roof structure, we want to set the magnitude here to negative 0.01 kips per square foot. The program remembers all my settings for my roof. Maybe I exclude the option down here to set the members parallel to member where it removes the influence from. I click OK, and now we should see this area load applied in the lateral direction here to our structure. Now, in reality, we'd probably want to apply some lateral loads to our columns as well, but for simplicity, we'll just move on with this lateral application. So under tools, we also want to maybe apply a downward load. And for this, again, we can just modify the load direction in the global Z direction, modify the magnitude to negative 0.005, and maybe we actually do want to exclude those intermediate beams here from my downward wind loads. I click OK. So all within this same wind load case 1, we can see a downward wind load along with the lateral load applied. Now, a nice trick is that for wind load 2, I'd like to essentially keep the same load application, but I just kind of want to modify either the magnitude or the load direction. So what we can do instead of going back and once again applying our area loads with the load generator is go to my load cases and combinations, and I'm going to take wind 2 and I'm going to completely delete it. So now when I take wind 1 and I make a copy and I rename to wind load 2, the benefit is that when I have already applied my loads to my load case, it will copy the loads along with the load case to wind load 2. So now when I click OK, I've copied all those loads from wind load 1, and you can see now I'm looking at wind 2. All I need to do is to double click at my top load here and reverse the orientation, reverse the magnitude here for an uplift force instead. So that's just a nice way to quickly redefine loads here by copying the actual load case itself. So now that we have defined all of our different load cases, we actually can scroll through to the different load combinations and see these applied to the structure at once, including live loads, impact loads, wind loads. Everything is shown here. Now, before we are ready to run our analysis, there is one thing that I want to discuss from the ADM, and this is the stability requirements according to section C2. So I actually did a previous webinar. It was around 2 years ago, but everything is still applicable to design today, according to the ADM 2015. And I went into much more detail about the stability requirements in Chapter C. So certainly refer to that on our YouTube channel or on our website. You can just search ADM and that will bring up that previous webinar. But today, what I do want to apply is the reduced stiffness requirements from section C2. And the code tells us that we do need to reduce the flexural stiffness by a tau sub b factor. And the tau sub b factor is an equation and it needs to be iterated based on the axial forces within our member. Additionally, there's a 0.8 factor that should be applied to bending and axial. And lucky for us, these requirements are almost identical to what the AISC requires. And what we have in the program, when we highlight all of our members, we can right-click to edit the member. And when this dialog box pops up, you'll see here a Modify Stiffness tab. Well, this allows us to modify the stiffness according to the AISC 360. Now, again, the ADM 2015 lines up exactly with the requirements from the AISC. We will determine what that tau sub b factor is, and we will also apply a 0.8 factor to the flexural and axial stiffness. So now this will be applied to all members that contribute to the lateral stability. It is also a conservative approach just to apply this to all members as well, including gravity members. So I click OK. And you might be asking yourself, well, okay, the stiffness reduction is great for my design combinations for the ultimate limit state, but for serviceability or for deflection, I don't want to reduce that stiffness. So how do we separate that out? Well, we can do so directly within our load cases and load combinations tab. So what I can do is to select all of my ASD load combinations here by holding down my shift button. Under the calculation parameters, we have the ability to uncheck the members here for the stiffness factors. So this will no longer reduce the stiffness for all of my ASD load combinations, which are typically used for deflection. But if we take a look at some of our LRFD load combinations, sure enough, that checkbox is activated again. So we will reduce the stiffness based on the stability requirements within the ADM. So now with that said, we are finally ready to run our calculation. So we go to calculate all, and the program is actually going to cycle through about 40 or so load combinations, again, running a nonlinear analysis to account for secondary effects of P delta and P little delta. So once this is done running, we will be presented with our results directly within RFEM. And we'll notice now that we will have a results tab available to us. And currently we're looking at the deformations of our structure, which is a little bit difficult to see here because it is just based on the center line. So under the display tab, this actually controls everything that we're viewing graphically here. We can turn on and off different elements. We can change the view. For example, the results tree here. We can expand out the deformations for members, and we can change this to cross sections colored. I can even smooth my color transition to make it look a little bit nicer here. And now I can scroll through to my different load combinations just to see the reaction of the structure under the different applied loads. And if we're also interested in seeing how the structure behaves as a short little video, we can play the animation here. And how I think this is useful is that if we incorrectly modeled something, we'd probably see some odd deflections here for this video. So just a nice feature that we can export this out, of course, and save to our computer as a video file as well. So in addition to deflections, probably what we're also very interested in is member internal forces. So we can go back to our results tab, and I can scroll in here to view these members in closer detail, and we can take a look at axial forces, shear forces, bending moments. These are all available to me graphically. I can also right-click on any one of these members to go to the results diagram. The results diagram will just essentially show me in a little bit more detail where I can turn on and off these internal forces and deflections, what's going on along the member length. I can also scroll through to different load combinations here, export them out to my printout report. So maybe a little bit more detailed than what we can see graphically here. In the same concept, we also can view our support reactions. So with the support reactions, we can turn those on graphically. And again, all this information is available to us within our tables. So we're currently looking at table 4.1 for support forces. You'll notice that the table synced up with RFEM here with the big red arrow showing me exactly where I'm at according to this table that I'm clicking in. So we can export all of this information, support reactions, internal forces, again, to our own design tools, such as Microsoft Excel, maybe some in-house tools to provide the design. But if we want to take it a step further within RFEM, then this is where we want to take advantage of our design add-on module, RF-ALUMINIUM ADM. So we can activate the add-on module within our project navigator over on the left, or we can access the add-on modules under our drop-down at the top. This is nice because they are categorized a little bit nicer, where we can go to design of aluminum per the ADM. Now, when I choose one of these add-on modules, notice that it's just a dialog box that pops up within our main program. I don't have to worry about remodeling any of this information or redefining cross-sections, materials, load combinations. It's all brought in. What we're doing here is specifying information that is specific to the ADM module, including things like unbraced lengths or which load combinations we want to consider for design. So I'd like to start off with a fairly simple case here for introduction into this module. And I'm going to rename my case here to secondary beams. I click OK, and I want to select the beams that I would like to design for this first case. Well, I want to design these intermediate beams. Now I can individually highlight these and select them, but a better option under the Views tab is to select my members by cross-section. And I will choose the 3x3 cross-sections, and now you'll notice that everything is grayed out within the rest of my model. So now I can easily highlight the entire model with only selecting those 3x3 cross-sections. We want to choose the LRFD 2015 for our design. And for our ultimate limit state, this is where we choose our LRFD load combinations. And serviceability limit state would be our ASD load combinations, again, brought in directly from RFEM, considering stiffness modifications and everything else that we've previously set. All we need to do now is to simply move down our list over on the left. The materials are brought in from RFEM. We're still utilizing aluminum 6061. We have our cross sections here with our 3x3 with the cross section properties shown. Intermediate lateral restraints, if we had any top and bottom flange bracing. Now this isn't so applicable, for example, today with tube structures, but maybe you had some type of I-beam as shown, then you would set the intermediate lateral restraints under this table here. The effective length. So this is our stability design. We have strong axis buckling, weak axis buckling, lateral torsional buckling, and flexural torsional buckling. So to explain a little bit about all of these different options, you'll notice here that we have the effective length factors. Well, section C3 from the ADM tells us that we can use K equal to 1.0 unless a smaller value can of course be justified. So we'll go ahead and leave all of these values set to 1.0. Now the effective length, which is our K times our unbraced length, is our next column here. By default, everything will go ahead and populate according to the member's length back in RFEM. So in this case, they're all 4.5 feet. Same thing for unbraced length in the weak axis direction. So if by chance you didn't model in some members here, or maybe those PV panels are bracing these members laterally, for both strong and weak axis direction, then you can go ahead and adjust the unbraced lengths here. But for today, we'll just keep all of those to default to the full member length. Lateral torsional and flexural torsional buckling are very interesting because we have the ability, again, to set unbraced lengths here for LW, which would be the lateral torsional buckling length, or LT, which is the flexural torsional or torsional buckling length. So if those differ from the full member length, you can adjust those here. Now, the critical buckling moment can be determined by default is an eigenvalue analysis. So this is a much more theoretical approach where we are essentially going to consider 4 degrees of freedom on either side of the beam member. Now, our assumptions with this is that the member is laterally and torsionally restrained at the ends, but free to warp. So if these are your constraints and you want to run it according to an eigenvalue analysis to determine the critical buckling moment, you can leave this as default. Typically, or I wouldn't say typically, but sometimes we find that maybe an eigenvalue analysis will give us quite a bit more capacity than what we'd find according to chapter F here. So in turn, if you'd like to use the analytical equations directly from the standards, then you can change that to according to F. Or manually, you can type in your critical buckling moment as well. So we'll leave this as an eigenvalue method for the stability calculations. Now, serviceability data, this is where I select the member reference within my dropdown, and then I graphically select all of the members here that I'm interested in for serviceability design. So I've highlighted all of these members, same thing that we're doing for ultimate limit state design. Now, the reference length, once again, defaults to the full member length. We can put in here a pre-camber. We specify if it's a beam or a cantilever. I'll show you in just a minute exactly where we set the limiting deflection ratios to, because we need to have something to compare this to, of course, to the deflections that the members are experiencing from the analysis. Under the parameters for members, so this is actually for tensile strength according to chapter D. And in section D3-2B, the code states that tension transmitted through some but not all of the cross section, if this is the case, then the effective net area A sub E needs to be calculated. And A sub E depends on eccentricity of the connection, the length of the connection, so you can see all of this input data here. And what we'll do within the program is to automatically calculate your effective net cross-sectional area, A sub E, which is ultimately used for the tensile rupture capacity. So if we do have that situation at either the member start or the member end, this is where we can reduce that area here. Under the details tab, quite a few options throughout here that we just really don't have time to go through today, but certainly the help file, which you can access with this little question mark down at the bottom, is efficient for giving a little bit more information on all of these settings. But under the serviceability tab, well, this is where we can set our limiting deflection ratio. So you can see L/360 is set for beams, L/180 is set for cantilevers, and you can override these limiting deflection ratios as you see fit for your design project. So once we have defined all of this information, we hit calculation, and you'll actually see that the program solves this rather quick because we already have all of our internal forces from RFEM. We're just bringing them into this add-on module, applying the ADM calculations, including the quick little eigenvalue analysis for stability, and then ultimately we're coming up with our results. Now we can view design by member. And again, when I'm looking at these tables, you'll notice that everything is synced up in the background. So I can take a look at this particular check. This big red arrow is telling me where the controlling internal force is for the axial check, for example, and biaxial bending according to chapter H. What's also really powerful is that for each member, we're giving you the results for every check within the ADM. So you're going to see here shear checks, bending checks, biaxial bending, axial forces, and of course, lateral torsional buckling and stability checks for biaxial bending. The reason why we do this is because we don't really want to be a black box program, but we're trying to give you as much information as possible so that you can understand where the numbers have come from. In addition, you'll see all of the variables listed here along with the code references. By all means, though, if we're not really interested in seeing all of this information, but we just want to know what is the controlling check for each member, well, we can easily use our filter option here to filter by max, and now we can see for each member exactly what's controlling. So in many of these cases, stability is controlling, and I just want to point out that for any one of these stability checks, we actually can view a picture here, a graphic of our mode shape. So this is what's going on in the background when it's running this eigenvalue analysis to determine the critical buckling moment. So just a nice feature to see what's going on there. Now, all of this information is available to us graphically, so we can click the graphics option. Now, we're within the RF-ALUMINIUM ADM module. We're just viewing these code check results graphically back in RFEM. So I can take a look at my ultimate limit state design, or if I want to turn off ultimate and view my serviceability limit state design visually, I can see both of those there. We also can go back to the ADM module and view a parts list by member. Again, all this information can be exported directly to Microsoft Excel. So that's just a quick introduction to the aluminum ADM module with a fairly simple example for these beams. The other quick example I want to show you is, of course, with our custom extruded sections that we brought in from ShapeThin, and how we can also design those within the module. Now, notice that the program has broken apart these members here based on where they were framing into the columns. And actually, that's not a big deal at all. So what we want to do here is, under the Views tab, I'm going to select all of my ShapeThin sections. And we'll turn off my 3x3 sections. I can highlight all of my members here. I can right click, and under member we have the opportunity to create sets of members. So what the program does is it groups these individual members into what's called a set of members, which just places a very faint dotted line around these segments. So you'll notice that I didn't have to clear my results for the analysis. It does not affect the analysis whatsoever that these are broken apart into separate segments. But for design, maybe we are interested in designing this as one continuous member rather than individual segments, which, by the way, both are possible. But I just want to show you the benefits of designing a set of members quickly. So we'll start off by designing our set of member that I've shown highlighted here. We go back to our RF-ALUMINIUM ADM module, and I'm going to go to File, New Case. For this one, I'm going to call this one Main Beam. I click OK. What the program gives me the ability to do is to always jump back to my secondary beam design. So I've just created a second case here within my dropdown. This time, I want to design my set of members here. I click OK. Now, quite honestly, not much is different with sets of members until we get to some of these later tables. I want to select all of my LRFD load combinations according to the LRFD 2015. Now, I will skip over serviceability limit state design just for the sake of time. So we'll only take a look at the ultimate limit state design. And then we're just simply moving from top to bottom with our tables here with materials. Notice the cross section for our ShapeThin custom extruded section is available here with all the cross section properties that we calculated way back when. The effective length. So this table looks slightly different than what we saw for members, and now is effective lengths for sets of members. And some things are grayed out here. And that's because everything is actually controlled under our next table for nodal supports. So similar to members, for sets of members, we are running an eigenvalue analysis for stability once again in the background. But what's more powerful about sets of members is that we have a bit more control over how we are specifying how those 4 degrees of freedom where our supports occur actually fixed or released. So we can see here under nodal supports, which is a new table for sets of members, our individual set of members here. And I can isolate this to take a look at the set of members and where the program has automatically placed these supports. Now, actually, this is not correct because I don't want to place a support on the right-hand side, but rather I need to move that back to where my lateral members are framing in as well as my column. Well, that's no problem. All I need to do is just to graphically select my new node here, move it back to node 26. And actually, let's go ahead and try that again. I want node 26 and I also want node 35. There we go. So I've supported this individual sets of members exactly where we have all these different members framing in. Now, this is where I have my 4 degrees of freedom that I have the control to set now for sets of members. I think we can all agree that we do have lateral restraint because we have these transverse beams framing in at both of these support locations. Rotational restraint is the ability for the member to rotate about its own axis. And I would also agree here that maybe we are restrained in that aspect as well. Now, rotation about the vertical axes. I would say that maybe for our front support here with our column framing in, we do have restraint about the vertical axes for rotation. Now, this is not applicable for our example today, but if we had warping restraint, we could also set that at any one of these supports. But let's not forget that we also have this back column framing in here. So I want to additionally choose this node and node number 29. It places a new support here, but the only degree of freedom that I would like to place at this location is the ability for the column to restrain rotation about the vertical axes. Everything else is pretty free to move because we don't have any lateral restraints framing in there. So now when we jump back to the effective lengths, you'll notice that my weak axis buckling, lateral torsional buckling, flexural torsional buckling, this is all controlled from those nodal supports that I just put in there. So again, much more control over the 4 degrees of freedom. What also is powerful about sets of members is that they don't necessarily have to be in a straight line. You can design a continuous member that doesn't lie in a straight line, but is in the same plane. So for strong axis buckling though, we do need to adjust this, and the worst case distance here is in between our 2 columns at 7.95 feet. So the last table here is member hinges. If we wanted to release any one of those 4 degrees of freedom along the set of members, we could do so here, but we don't have that for today's example. So then I can just click calculate. Again, it solves within a quick second, and we're presented with our results, and we can view design by sets of members. So same concept here. We're going to present to you all of the different checks directly within the standard. And I wanted to point out a course stability analysis for lateral torsional buckling. And we can view our mode shape here for this set of members and what the program's actually doing in the background. One thing I mentioned over and over again is the ability to check local buckling for these custom extruded sections. So that work that we put in within shape thin for the element with the thickness ratios and whether it's closed or open on either end, well, you can see here that that's now all listed under the cross-section local buckling. So every single element is listed here. It shows whether it's in tension or compression, how it's classified, the slenderness. So again, very powerful because not a lot of other programs have the capability. Of course, we can bring it in, we can do general design, but the ability to do local buckling for all of these individual lips and webs and flanges is pretty powerful. Okay, so that's essentially what I wanted to quickly show you for design by sets of members, and that will actually bring us to the end of our webinar today. So jumping back to the PowerPoint, as always, I know that this is a lot of information within the hour, so feel free to visit our website at dlubal.com to learn more information about RFEM, shape thin, and the add-on modules. We also have our web shop listed there so you can see pricing information on any of these products. I certainly want to encourage everyone to follow us on our social media accounts. You heard me mention our YouTube channel. Well, this recorded webinar will be placed on there within a day or two, so you can review everything that we learned today as well as other previous webinars. Same thing for LinkedIn, Twitter, Instagram. We like to announce there different events and conferences that we've been at, technical articles, frequently asked questions, so it can be really useful for your time spent in RFEM. Now, if you have any questions about today's webinar or any other question about our products, please contact us in our Philadelphia office at our email listed here, info-us@dlubal.com, and our phone number is 267-702-2815. So we will have many more upcoming webinars. We try and do them about once a month. You can register on our website at dlubal.com under support and learning and webinars. But as most of you know today, I send out a reminder email about a week before these will occur. So feel free to register as those come up. Now, as for PDH certificates, these will automatically be emailed to all participants today. So they are available for participants who were here for the full presentation. This just is required by the different states that we are allowed to present PDH certificate to you guys. Of course, there's some leniency by several minutes, so no problem there. If there were any attendees that attended but did not register with your own email and your own name and you are wanting PDH, you will have to request that. And you can send us an email at info-us@dlubal.com. So again, if you yourself did not register with your own name and your own email, the only way to get a PDH certificate is to go ahead and send us an email at the address shown here and request that. So as always, I want to thank everyone for attending today's webinar, and we hope to see you at our next presentation. Thank you.